For the function y equal to e of x, y prime will be just e of x. Now, if we have a composite function y is equal to e of u, then y prime will be equal to e of u multiplied by u prime. For the function y equal to ln of x, y prime will be equal to 1 over x. For the composite function y equal to ln u, y prime will be equal to 1 over u multiplied by u prime. So it's basically y prime is equal to u prime over u. Now, the function y is equal to log base a x, y, which can be written as ln x over ln a. We know that ln a is a constant. If it's a constant, we can pull it out, so it's y is equal to 1 over ln a multiplied by ln x. And we know that ln x as a derivative is 1 over x. ln a as a constant will not change, so it's 1 over ln a multiplied by 1 over x. Grouping them together, it's 1 over x ln a. For the composite function, y is equal to log base a of u, y prime will be equal to 1 over u ln a times u prime. Now for the proof, you need to recall that the derivative is the limit of f of x plus delta x minus f of x divided by x plus delta x minus x, which is delta x, as delta x approaches 0. We're going to apply the same thing with y is equal to e of x, so it's going to be the limit of e of x plus delta x minus e of x divided by delta x as delta x approaches 0. We are going to do some algebraic manipulation with the fraction. We'll go back to the limit. Now, let's factor out the e to the x. We'll get e to the delta x minus 1 divided by delta x. We can therefore rewrite the limit as the limit of e to the x times e to the delta x minus 1 over delta x as delta x approaches 0. Now you may remember that E is a special limit. It's the limit of x plus x plus 1 to the 1 over x as x approaches 0. This is how we discovered E. Therefore, if x is equal to delta x, x is approaching the values of delta x, which means that it's very close to 0. Now let us go back to the limit, and we're going to replace E by its value. So it's delta x plus 1 to the 1 over delta x. Okay, and this is E to exposed to delta x. We have our delta x approaching 0. E to the delta x is really delta x plus 1 multiplying the exponent. It's delta x over delta x, which is really 1. So E to the x is approaching delta x plus 1. So the limit of E to the x times, well, delta x is approaching 0. Delta x plus 1 for E to the delta x minus 1 divided by, the division will be done with delta x. Okay, so it's gonna be E to the x delta x over delta x delta x will cancel, so our answer will be E to the x. And we got y prime is equal to E to the x, which we should retain as a formula. The next one will be to prove that if y is equal to ln x, y prime is equal to, well, it's 1 over x, but we put in a question mark. Y is equal to ln x. We're going to take the exponential of both sides. E to the y is equal to E to the ln x, or E to the ln x inverse function is equal to x. Now let's just write inverse function. So basically E to the y is equal to x. Taking the derivative of both sides, the derivative of E to the y is, okay, we're gonna take the derivative of both sides. The derivative of E to the y is e to the y times y prime, composite function, and the derivative of x is just 1. So now to get y prime, we'll just divide by e to the y, and we'll get 1 over e to the y. Since e to the y is equal to x, we can just replace it. We got it right here. So we can just replace it, and y prime is equal to 1 over x. So we just showed that the derivative of ln x, if y is equal to ln x, the derivative y prime is equal to 1 over x. Let's take care of y equal to log base a of x, which is equal to ln x over ln a. Change the base. ln a is a constant. You just write it down again so we can pull it out. It's going to be 1 over ln a times ln x. Now when we take the derivative, the constant will not go anywhere, it won't change. It's going to be 1 over ln a, and the derivative of ln x, we know the derivative of ln x is 1 over x. Now y prime, we can switch them around. It's 1 over x ln a. It's more practical this way. Here we go.